for this problem, we want to relate the angular velocity to the radius and height of a certain container given a fluid. So for this diagram I've written out, we have the variable h, which is the height of the container, and the variable r for the radius of this container. This container is three-dimensional. I've just drawn it two-dimensional. It just makes things a whole lot easier. So what do we know? The first thing that comes to my mind for this is this obvious curve we see when we start to spin this container around its center point. So we're not, I don't want to say like stirring the container, we're not moving the container around. The container is sitting perfectly on a point and is spinning. It doesn't change its location, it just spins. So the first thing I see is this obvious push around, and that would come from the centrifugal force pushing that water to the sides and creating this opening in the center. So we can relate that with pressure. So we will get this equation. dP dr is equal to the density of the angular velocity over the radius. So this basically just means the density of the water multiplied by the centrifugal force, that pushing to the side. This equation is separable, and we can easily integrate this equation, so allow me to do that. So we have our bounds from 0 to p dp, which will just end up being p. We have the density and the angular velocity out front, and we have this 0 to big R. So little r is just some point along our bounded radius, and then 0 to r is the radius, essentially, where 0 is the center point and r is the maximum radius. So let's finish up the integral. So we get our rho, our density, our omega squared, our r squared over 2. So we have our omega, which is what we want, and we have our radius, but we also want to relate this to height. And it's not there, so we're not done yet, but this is related to pressure. And we do know another pressure equation that we can relate this to and solve some variables for, and that is rho GH. In this equation, I'm going to solve for h. However, this is not the h we want, but it could be beneficial for later, and I'll explain why. So we get that this height, and I'll explain that in a second, is equal to the angular velocity squared times radius squared over 2g. G is obviously gravitational acceleration. This height, however, is not the height of the container, it is the height of the fluid. Now, I'm going to explain this a bit more because you'll notice that if r is 0, everything becomes 0. So it can't be related to one of these two, but which one is it related to? So you'll notice as r changes, the height changes with it. So that means it can't be related to this one, which means it's related to this container. And you'll obviously know that because this requires an angular velocity. If it's 0, everything's 0, which means it can't relate to this container, that's related to this container. So let me draw a line to help explain this. So this height is the height of the fluid giving it spinning. So at the center here, you're not really spinning. At the center, you're a perfect point that exists in, it's like if I spin the center of this marker in the palm of my hand, the center of that marker really isn't spinning. That's the axis that it spins on around a point. So right here is exactly 0. But you'll notice that there's this difference in height over here, which is important to take note of. So we're going to call that difference D for difference or dip, whatever you want to call that. Now, this bottom portion right here, these volumes are equivalent. Pretty self-explanatory. That lower part of liquid really isn't moving. It's the same volume, same liquid. No liquid has escaped this system either, which means that this top part up here and this displaced liquid, while it's spinning, is also the same volume because no liquid is escaping. We're spinning this to the perfect point where the liquid is just at the rim of the container but not escaping. So we want to figure out this relationship. The first obvious one we can figure out the volume of the liquid over here. So we can write that equation in. Pi r squared times v. That dip is just acting as a height here. Pi r squared, this is obviously a three-dimensional container like I said earlier. 2D is just easier to draw. So that's cool, but isn't really helping us anywhere with this equation. We could plug in for r squared, but that's not helping us get this maximum height. So we need to figure out a different one. So how would we figure out the volume of this equation? Well, we'd have to do this, and let me draw it out to help explain this. So I basically took that top half of this line from this part up. I'll shade it in for you. I took that portion, pulled it over here. So like I said earlier, according to the fluid height equation, this center point right here is 0. So I put a little 0 there. And I took out what appears to be 2 chunks from this. And now those aren't 2 independent chunks. I basically took out a ring from this 3-dimensional container. So if this over here is our container, I took out a portion of a ring where this is obviously our 0, and we want to do that a bunch of times. So we're going to take essentially an integral. So allow me to write out this equation for you. Voila. So that means that this volume is equal to 2 pi h over the, not over the radius, but times the radius. And now we can integrate this and see what that gets us. If you notice the problem right away, congratulations. This h is a problem. However, this h represents the height of our fluid, as I've been saying this whole time. And we have it right here. So all that's left is to plug it in, see what cancels out, and see if we can continue with this integral. Two things to note before I integrate this. You'll notice there's no bounds for this dV. This dV is bounded by the volume, but that volume never actually changes. So it's just bounded by, say, V. However, there's no way that there's no volume here, because we know the volume is a constant. We know it's just this number. So it's really hard to put bounds on this part when you know it's just going to end up being V for V. And then secondly, although it's big R in this equation and little r in this equation, this r just represents some value along this bounded r. So it'll eventually become bounded r again after I integrate. However, r can represent big R, but big R can't represent little r. So that's why this is a little bit interchangeable. But with all that being said, I'm just going to proceed to integrate now. So we get that the volume on this side is equal to pi omega squared r to the fourth power divided by 4 times the gravitational acceleration. Still, we do not have height here. However, we do have the relationship. We know these volumes are the exact same volume because of mass balance. So we know that we can set these equal to each other and solve for d. And I'll explain why we solve for d in a second here. Just allow me to work this one out. So we get that this distance, displacement, or dip, is equal to omega squared r squared over 4 times the gravitational acceleration. Why did I solve for d? Well, you might notice that the total height of this container is equal to the fluid height plus the radius minus this dip. Radius is just representative of this original fluid height, the change in the fluid height. That change in the fluid height is represented as dip. So this equation I'll just put that sub r there so you know which h I'm talking about. So we can proceed to plug in some values here really quickly. That looks good. So, you'll notice here, I may have put these parentheses, but the parentheses really don't matter, just a grouping thing to keep consistent with the parentheses I had up here. R will eventually be moved over. You'll notice that this is just a negative fourth, a positive half. This will leave us with a positive 1/4, which means this will be written out really easily. So I'm just going to make some space over here where the fluid height was so I can write this out for you. So, for this final answer, we get that the angular velocity that we have to spin this fluid at to reach that maximum displacement without spilling any fluid outside of this container is related to 2 times the square root of the gravitational acceleration times the difference in the height minus the radius divided by the radius of this container. This is the relationship of the angular velocity and the height and radius of a given container. That is all for this video. Thank you for watching.